Tonight we travel beyond the familiar stars into the quiet mysteries of deep space, where strange worlds, silent wonders, and cosmic secrets drift in the dark. Far from the warmth of ordinary skies, the universe becomes quieter, colder, and far more mysterious than we often imagine. And tonight, our journey begins with a signal that came from billion light years away. So settle in, let the noise of the day fade away, and drift with me into the deep silence of the cosmos. There is a particular kind of silence that exists between galaxies. It is not the silence of an empty room, or the silence of a forest at night, or even the silence of deep ocean water pressing down from above. It is something older than any of those things, something so vast and so complete that the human mind, when it truly tries to comprehend it, tends to slip sideways into a kind of quiet awe that feels almost like sleep. This is the silence of intergalactic space, the unimaginable distances between island universes, each one containing hundreds of billions of stars, drifting apart from one another across a canvas so large that even light, the fastest thing in the known universe, requires billions of years to cross it. And it is into this silence, this ancient and unfathomable darkness, that the signal arrived. Not a whisper, not a hum, a burst, sharp, brilliant, catastrophically brief, lasting only a fraction of a second, yet carrying within it more energy than our own sun will release across an entire decade of its long and steady life. It crossed billion light years of space to reach us, and when it finally did, it arrived as a single, fleeting pulse of radio waves, detected by instruments we only recently became sophisticated enough to build. The universe had been holding this message for longer than Earth itself has existed, and it delivered it in less time than it takes to blink. To understand what this means, to truly sit with the weight of it, we must first understand the nature of the thing that sent it. We must understand what kind of event could produce such an extraordinary release of energy across such an extraordinary distance. And to do that, we must travel backward in time, not metaphorically, but literally, because that is precisely what looking out into deep space requires of us. When astronomers point their most powerful radio telescopes at distant regions of the sky and detect a signal from billion light years away, they are not observing something that is happening now, in this present moment, in this sliver of cosmic time we call the contemporary universe. They are observing something that happened billion years ago, in a universe that was younger than it is today by more than half its current age, in an epoch when the cosmos was still arranging itself, still building the large-scale structures we now call galaxy clusters, and cosmic filaments, still burning with a density of star formation that has never since been equaled. This is a message from a younger universe, a more turbulent one lit from within by forces we are only beginning to understand. And the signal itself, this fast radio burst, as astronomers call it, is one of the most mysterious and most studied phenomena in all of modern astrophysics. Fast radio bursts, or FRBs, were not a part of the scientific vocabulary until relatively recently in the long history of astronomical discovery. The first confirmed detection of such an event occurred in Chi, when astronomer Duncan Lorimer and his student David Narkovich were reviewing archival data from the Parkes radio telescope in Australia, sifting through records collected back in E, when they encountered something extraordinary buried in the numbers, a single, intensely bright pulse of radio emission that had lasted only a few milliseconds and had displayed a very particular characteristic called dispersion. Dispersion? meaning that the higher frequency components of the signal had arrived slightly before the lower frequency ones, exactly as would be expected if the signal had traveled through a large amount of ionized plasma, which is precisely what fills the vast spaces between galaxies. This dispersion measure, as it is technically known, was so large that the source of the signal could not have been anywhere within our own Milky Way. It had to have come from cosmological distances. It had to have come from somewhere genuinely, almost incomprehensibly far away. That event, now called the Lorimer burst, opened a door in astronomy that has not since been closed, and through that door has poured one of the most vibrant and bewildering fields of modern astrophysical research. In the years following Lorimer's discovery, the scientific community was cautious. A single data point is not a pattern. A single unexplained event could be instrumental error, terrestrial interference, a satellite passing at exactly the wrong moment, any number of mundane explanations that astronomers are always obligated to consider before reaching toward the extraordinary. But then more bursts were detected. And then more. And then, as new radio telescope arrays came online, instruments of increasing sensitivity and sophistication capable of monitoring larger swaths of sky with greater precision than any previous generation of technology had allowed, the detections began to accumulate in earnest. By the early Arsenling-Arserses, astronomers had catalogued hundreds of confirmed fast radio bursts, and the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, which began full operations in Arsenling-Isherbat from its site in British Columbia, was detecting new ones at a rate that sometimes reached one per day, revealing a universe far more alive with these mysterious pulses than anyone had initially imagined. The sky, it turned out, was full of them. They were arriving from all directions, from all distances, from galaxies near and far, each one a brief and violent cry from some unknown source, embedded in the fabric of the distant cosmos. The signal that forms the heart of this story belongs to a category of fast radio burst that pushed the boundaries of what astronomers thought possible in terms of sheer detectable distance. When a team of researchers, working with data from the Australian Square Kilometre Array Pathfinder, a remarkable instrument known by its acronym ASKAP, consisting of 36 dish antennas working in concert across the flat, radio-quiet landscape of Western Australia, announced the detection of a fast radio burst that had travelled approximately billion light-years to reach us. It represented not only a new record for how far such an event had been traced, but also a profound and layered scientific achievement that touched on questions far larger than the burst itself. The event was catalogued under the designation FRB, Arsenling-Arser-Arwenling Lopbike Isher A, and its identification and analysis were published in the journal Science in October. Arsenling-Arsersan, representing the work of dozens of researchers across multiple continents and institutions, all united by the desire to understand this brief, ancient pulse that had crossed half the observable universe to reach their antennas in the Australian desert. The distance was not a guess. It was not an approximation pulled from theoretical modeling alone. It was derived from the burst dispersion measure, that telltale spreading of frequencies that encodes within it the total amount of matter the signal passed through on its journey, and then confirmed through the painstaking process of identifying the host galaxy from which the burst originated, measuring that galaxy's redshift using optical telescopes, and calculating from that redshift the true cosmological distance the signal had traveled. At a redshift of approximately e, meaning the universe has expanded to roughly twice its size since the signal was emitted, but billion light-years is not poetic license. It is physics, it is geometry. It is the universe stating its own dimensions in the only language it has ever spoken. What makes this particular detection so remarkable? What elevates it from being merely a record-setting event to being something genuinely transformative for our understanding of the cosmos is what the signal's journey can tell us about the matter that fills the space between galaxies. For decades, cosmologists had confronted a quiet but persistent embarrassment in their accounting of the universe's ordinary matter. When they added up all the matter they could see, the stars, the gas clouds, the dust, the galaxies, the galaxy clusters, and compared it to the amount of ordinary matter their best cosmological models predicted should exist based on observations of the early universe and measurements of the cosmic microwave background, they found a discrepancy. Roughly half of the universe's ordinary baryonic matter appeared to be missing, unaccounted for, invisible to every instrument trained upon the sky. Theoretical models had long suggested that this missing matter was not truly missing, but merely hiding, dispersed so thinly across the vast voids between galaxies in a warm, diffuse, highly ionized state that it was essentially transparent to visible light and nearly impossible to detect directly. This hypothetical material had been given the name Wu-Him for warm-hot intergalactic medium, and its existence had been predicted with considerable confidence by simulations of large-scale structure formation. But actually detecting it, actually measuring it, and confirming it observationally had remained one of the great open challenges of observational cosmology. Fast radio bursts, it turns out, may be the key to solving that mystery, and the burst that traveled about billion light-years brought that key closer to our grasp than ever before. The logic is elegant in the way that the best scientific insights tend to be, simple at its core, even if it's technically demanding. A fast radio burst, as it travels across intergalactic space, passes through every cloud of ionized gas, every filament of diffuse plasma, every thin veil of the Wu-Him that lies along its path. Each encounter with this material adds a small but measurable delay to the lower frequency components of the signal, incrementally widening the dispersion measure in a way that depends on the total column of electrons the signal has traversed. By measuring the dispersion measure of a fast radio burst, and then independently measuring the distance to its host galaxy through optical observations, astronomers can calculate how much ionized matter the signal passed through per unit of distance. And from that, they can begin to reconstruct the average density of matter in intergalactic space. Repeat this process across many bursts from many distances, across many bursts from many distances, and you begin to build a statistical picture of the universe's missing matter, tracing it not through direct observation, but through the fingerprints it leaves on signals passing through it across billions of years of cosmic time. This technique was first described theoretically in Relation by astronomer J.P. Macquart and colleagues, and the relationship between dispersion measure and distance that it predicts has come to be known as the Macquart Relation, a foundational tool in the emerging science of using fast radio bursts as cosmological probes. The burst from back billion light-years tested this relation at a distance never before achieved, and in doing so, it extended our empirical knowledge of the universe's matter distribution deeper into cosmic history than any previous observation of its kind had managed to reach. But before we can fully appreciate what the detection of FRB, Arsenling Arser Arwenling Lope Isher A means for cosmology, before we can absorb the implications of using an ancient radio pulse as a measuring tape stretched across half the observable universe, we must spend some time with the source itself, with the question that has haunted fast radio burst research since the very moment Lorimer first pulled that anomalous signal from archival data and realized he was looking at something for which science had no ready explanation. What produced the fast radio burst? What kind of object? What kind of event? What kind of physical process could possibly generate a pulse of radio emission so intense that it remains detectable across billion light-years of expanding space, arriving at our instruments with enough energy to be distinguished from the background noise of the cosmos, yet lasting only milliseconds, sometimes only microseconds, before vanishing as completely and as suddenly as it appeared? This is not a trivial question, and the history of attempts to answer it is a story of scientific imagination operating at its fullest stretch, proposing mechanisms both conservative and radical, both familiar and genuinely alien, as the community wrestled with an observation that seemed to defy easy categorization. In the early years of FRB research, before the catalogue of known bursts had grown large enough to reveal patterns and before any burst had been localized to a specific host galaxy, the theoretical landscape was almost chaotic in its diversity. Dozens of models were proposed, ranging from the mergers of compact objects like neutron stars to the evaporation of primordial black holes, predicted by Stephen Hawking's theoretical work, to the collapse of neutron stars into black holes, to the interactions of pulsars with their surrounding environments, to, in a small number of genuinely speculative proposals that were quickly noted, and just as quickly set aside, the possibility of an artificial origin, some technological process associated with an advanced civilization using radio emission, at cosmological scales, for purposes we could not begin to guess. Science is obligated to consider all possibilities before eliminating them. But the weight of evidence, as it accumulated, pointed not toward the exotic or the artificial, but toward something that was, in its own way, even more extraordinary. The magnetar. A magnetar is a type of neutron star, and a neutron star is itself already one of the most extreme objects. That physics permits to exist within the known laws of nature. When a massive star, one with perhaps 8 to 20 times the mass of our own sun, reaches the end of its nuclear fuel supply and can no longer sustain the outward pressure of fusion reactions against the inward pull of its own gravity, it collapses in a catastrophic implosion that releases more energy in a few seconds than the sun will emit across its entire 10 billion year lifetime. The outer layers of the star are blasted away in a supernova explosion of extraordinary violence, while the core is compressed to a density that strains the imagination. A sphere perhaps 20 kilometers across, containing more mass than the sun, so dense that individual protons and electrons are forced together to form neutrons, and the resulting object is essentially a single atomic nucleus of city-sized proportions, held up not by any familiar chemical or atomic force, but by the quantum mechanical pressure of neutrons resisting further compression. Neutron stars rotate rapidly, often spinning hundreds of times per second, and they carry magnetic fields of immense strength, typically somewhere between 10 to the power of 11 and 10 to the power of 13 Gauss, compared to Earth's magnetic field of less than 1 Gauss, and the sun's of a few Gauss. These objects are already so far beyond everyday physical intuition that they seem to belong to a different universe than the one we inhabit. And then there are magnetars, a subset of neutron stars whose magnetic fields are not merely strong, but almost incomprehensibly powerful, reaching strengths of 10 to the power of 15 Gauss or beyond, making them the most intensely magnetized objects known to exist anywhere in the cosmos. The magnetic energy stored in a magnetar is so enormous that it literally deforms the neutron star's crust, causing it to crack and shift in starquake events that release bursts of high-energy radiation, and in some cases, under conditions that theorists are still working to fully characterize, producing the kinds of coherent radio emission that could, under the right circumstances, explain the phenomenal energy output of a fast radio burst. The case for magnetars as the engines behind fast radio bursts was dramatically strengthened in April, Arsenling Arsers, when astronomers detected something that had never before been observed, a fast radio burst, originating not from a distant galaxy, but from within our own Milky Way, close enough to be localized with precision to a known magnetar called SGR, Ichenjubyte Sensurwuhlas Arsenibyte Wushersus, located approximately censures ling light-years from Earth in the constellation Vulpecula. The detection was made simultaneously by multiple instruments, including the KIME telescope in Canada and the START RRA in the United States, and the burst's properties, its intensity, its duration, its dispersion characteristics, placed it firmly within the fast radio burst category, providing the first direct observational link between a specific, identified compact object and the FRB phenomenon. If a magnetar within our own galaxy could produce a signal of this nature, then magnetars in distant galaxies, viewed across billions of light-years of space, could plausibly account for at least a significant fraction of the fast radio bursts catalogued from cosmological distances. This did not close the question entirely. The diversity of observed FRB properties, the existence of so-called repeating bursts that return from the same location, multiple times, and non-repeating bursts that appear only once and never again, the range of energies and durations and spectral characteristics across the growing catalog all suggest that perhaps not all fast radio bursts share a single origin, but it provided a foundation of observational evidence solid enough to anchor the magnetar hypothesis at the center of theoretical discussions, giving researchers a concrete physical model to test and refine as new data continued to arrive. The burst from billion light-years, FRB, Artsendling Arser Arwenling Lubat Isher A, fits comfortably within the magnetar framework, though with one notable and scientifically interesting complication. Its energy output, calculated from its observed brightness and its enormous distance, was exceptionally high. Higher, in fact, than most previously detected bursts, placing it among the most energetic fast radio bursts ever recorded. This is not necessarily a contradiction of the magnetar model, since the range of magnetar properties in the universe is expected to be wide, and younger magnetars, those formed more recently from supernova events, may carry substantially more magnetic energy than older ones, allowing them to produce more intense bursts. But it does raise a question that the scientific community has not yet fully resolved: whether there exists a population of sources capable of producing fast radio bursts at the extreme high end of the energy distribution that may require mechanisms beyond what a standard magnetar starquake can provide, or whether the magnetar model, in its full theoretical complexity, is capacious enough to account for even the most energetic events. This is the kind of question that keeps astrophysicists engaged, but that drives the design of new instruments and the planning of new observations that ensures the field of FRB research will remain one of the most active and productive areas of astronomy for years and decades to come. There is something deeply moving, if one pauses to consider it, about the chain of events that connects the source of this signal to its detection. Somewhere in the early universe, in a galaxy we can now identify only as a faint smear of light. In deep optical images obtained by the Very Large Telescope in Chile, a star lived its life, fused hydrogen into helium, and helium into carbon, and carbon into heavier elements in a sequence of nuclear burning stages that played out across millions of years and then collapsed and exploded in a supernova that left behind a neutron star of extraordinary magnetic intensity. That magnetar, newly formed and burning with the energy of its creation, experienced some kind of violent event, a starquake, a sudden reconfiguration of its internal magnetic field, a catastrophic release of stored magnetic energy. And in that moment, it emitted a burst of radio waves carrying more energy than any process in ordinary stellar physics produces. Those radio waves expanded outward in all directions, at the speed of light, spreading through the magnetar's home galaxy and then out into intergalactic space, passing through thin clouds of ionized gas in the vast filaments of the cosmic web, crossing voids of nearly perfect emptiness, hundreds of millions of light-years across, traversing the entire span of half the observable universe across. But billion years of cosmic time, during which the universe itself continued to expand, stretching the wavelength of the signal slightly as it traveled, redshifting it toward longer wavelengths in a way that encoded within the signal a record of the universe's own expansion history. And then, on a morning in June, those ancient radio waves, already a billion years old, already older than our solar system, reached the western coast of Australia and were captured by the 36 dish antennas of the ASKAP telescope, converted into digital data, streamed to computers, processed by algorithms, and flagged as an anomaly worthy of further investigation by a team of astronomers who recognized in the numbers the outline of something extraordinary. That chain, from magnetar to antenna, from the early universe to a server room in Australia, is one of the most remarkable passages in the history of human observation, and it deserves to be held in the mind with something approaching reverence. Approaching severance, the localization of the burst to its host galaxy was itself a technical achievement of considerable sophistication, and it represents one of the areas in which the ASKAP telescope holds a particular advantage over other radio instruments. Because ASKAP consists of multiple dish antennas spread across a baseline of several kilometers, it functions as an interferometer, an instrument that combines signals from multiple receivers to achieve an angular resolution far greater than any single dish could provide. By carefully measuring the tiny differences in arrival time of the burst signal at each of the 36 antennas, astronomers can triangulate the position of the source in the sky with a precision of arcseconds, a level of accuracy sufficient to identify which specific galaxy in a crowded field of optical objects is the true host of the burst. This process of localization, technically demanding and computationally intensive, is what elevates a fast radio burst from an anonymous pulse of unknown origin to a scientifically useful cosmological probe. Because only by knowing where a burst came from and how far away that location is, can astronomers extract the full range of information the burst carries about the matter it passed through on its journey. In the case of FRB, Arsienling Arshu Arwenling Lupai Isher A, the localization pointed to a host galaxy at redshift z equals approximately e, and follow-up optical observations with the Very Large Telescope confirmed both the identity of the host and its distance, completing the chain of evidence needed to establish this burst as the most distant, fast radio burst yet localized to a specific galaxy at the time of its publication. Refans
to appreciate the full significance of what localization means in the context of fast radio burst science, it helps to understand something about the history of astronomical discovery more broadly, specifically, the pattern that repeats itself again and again across the centuries of human skywatching, in which the detection of a new phenomenon is only the beginning of understanding. And the true scientific harvest comes only when that phenomenon can be precisely located, traced back to a specific source, and placed within the larger context of the universe's known structures and populations. This pattern played out with X-ray sources in the Ichenj-an Ichotirshes, when the first satellite-based X-ray X-ray telescopes revealed a sky blazing with high minus. Energy emission from objects that ground-based optical telescopes could not readily identify, and years of painstaking cross-matching between X-ray positions and optical images were required before the true nature of those sources. Neutron stars, black holes in binary systems, hot gas in galaxy clusters became clear. It played out again with gamma-ray bursts, those brief and violently energetic explosions first detected by military satellites monitoring the atmosphere for nuclear tests, whose origin remained one of the great mysteries of astrophysics for nearly 3 decades until the Beposax satellite. In Ichenj-T provided precise enough positions to allow optical telescopes to identify fading afterglows in distant galaxies, definitively establishing that gamma-ray bursts were cosmological in origin and among the most energetic events in the known universe. And now it is playing out once more with fast radio bursts. As the community moves from the era of detection into the era of localization, from cataloging pulses to understanding their sources, from measuring dispersion to mapping the matter of the cosmos, FRB, Arsienling Arsha Arwanling Lupai Isha A represents a milestone in this progression, not the end of the journey, not the final answer to any of the field's deepest questions, but a clear and unmistakable step forward into territory that was, only a few years ago, barely beyond reach. The host galaxy of FRB, Artsenling Arsa Arwen Ling Lubite Isher A, is not a dramatic object in the way that quasars or starburst galaxies are dramatic. It does not blaze with the light of a light trillion suns or shoot jets of relativistic plasma across hundreds of thousands of light years. It is, in the optical images obtained by the Very Large Telescope, a relatively compact and apparently unremarkable galaxy at a cosmological distance, one member of what appears to be a small group of galaxies that may be in the early stages of interaction or merger. This environment is scientifically interesting in its own right, because the conditions within and around interacting galaxies are often different from those in isolated systems. Star formation rates can be elevated by the gravitational perturbations that accompany galactic encounters, and the production of massive stars, the progenitors of the neutron stars, and magnetars that may produce fast radio bursts can be substantially enhanced. 3. The fact that at least some localized fast radio bursts appear to originate in environments associated with active star formation or recent star-forming activity is consistent with the magnetar hypothesis, since magnetars are expected to be young objects. forming from the core collapse of massive stars that have short lifetimes measured in millions rather than billions of years, and their most energetic activity is thought to occur in the early phase of their existence when their magnetic fields are strongest and most prone to the kinds of internal instabilities that trigger bursts. Reading the environment of a fast radio burst's host galaxy is therefore not merely an exercise in cataloging, it is a way of testing theoretical models, of checking whether the universe's actual behavior matches what our equations predict, of closing the loop between observation and theory in the disciplined and iterative way that defines the scientific method at its best. But the host galaxy tells only part of the story, because the signal itself, that millisecond pulse of radio energy that traveled a billion light years, carries within it a record not just of its origin, but of everything it encountered along the way. And it is this record, encoded in the structure of the signal's dispersion, that makes fast radio bursts such powerful cosmological tools. To understand how this encoding works at a deeper level, it helps to think about what happens to a radio signal as it propagates through ionized plasma. Radio waves, unlike light at optical wavelengths, interact measurably with free electrons, the charged particles that fill the ionized gas of intergalactic space. Else, when a radio wave passes through a region containing free electrons, the electrons respond to the oscillating electric field of the wave, and this response introduces a frequency-dependent delay. Lower frequency waves are slowed more than higher frequency ones, causing the pulse to arrive spread out in time, with its high-frequency components detected first and its low-frequency components detected slightly later. The magnitude of this spread, the dispersion measure, is directly proportional to the total number of free electrons along the line of sight between the source and the observer, degraded over the entire path length. This means that a burst from a greater distance passing through more intervening plasma will show a larger dispersion measure than a burst from a nearby source, all else being equal. By measuring the dispersion measure of FRB, Arshen Ling Asrawan Ling Lot by Isha A, and subtracting the contributions from electrons within the Milky Way and within the host galaxy itself, both of which can be estimated through independent observations and models, astronomers can extract the dispersion measure contribution from the intergalactic medium alone, and from that number, derive a constraint on the average electron density of the cosmos along that particular line of sight across a billion light-years of space. And this is the essence of what has come to be called the Macquart Relation, named for Jean-Pierre Macquart, the Australian astronomer who contributed enormously to the theoretical framework for using fast radio bursts as cosmological probes, and who passed away in Ursenling far too early, before he could see the full flowering of the field he had done so much to cultivate. The relation he and his colleagues formalized predicts that the average dispersion measure of a fast radio burst should increase with its cosmological distance in a way that depends on the average baryon density of the universe, the density of ordinary matter filling intergalactic space. If the missing baryons are truly out there, dispersed through the filaments and sheets of the cosmic web in the form of the warm, hot, intergalactic medium, then they will contribute to the dispersion measures of fast radio bursts traversing that medium, and by measuring enough bursts across enough distances, astronomers can statistically constrain the total amount of this hidden matter and determine whether the accounting finally balances. The results so far, including the analysis of FRB, Arsenling Arsarawan Ling Lutbat Isha A, and the ensemble of bursts, published in the landmark Earth's Nature paper by Macquart and colleagues, suggests that the answer is yes, that the missing baryons are indeed present in the intergalactic medium, that the cosmic budget of ordinary matter is closer to balanced than previously measurable, and that fast radio bursts are providing us with a tool to probe the large-scale distribution of matter in the universe in a way that no other observational technique has managed to achieve with such clarity and directness. It is a result of profound cosmological significance, and it was reached not through one grand observation, but through the patient accumulation of many individual detections, each one adding another data point to the statistical picture, each one contributing its tiny piece to the enormous mosaic of our understanding. There is a dimension of this story that deserves its own moment of quiet attention, and that is the dimension of time, not the light travel time of a billion years, which we have already contemplated, but the human time of scientific progress. The decades of theoretical work and instrumental development and observational patience that were required before humanity was capable of detecting, localizing, and interpreting a signal of this kind. The mathematics describing the dispersion of radio waves in plasma was well understood long before any fast radio burst had ever been detected. It is a consequence of basic electromagnetic theory that was worked out in the early decades of the 20th century, applied to pulsar studies in the liquors, and extended to cosmological applications in theoretical papers written years before ASKAP. Came online, or KIME began its systematic survey of the northern sky. The theoretical infrastructure was waiting, patient, and ready for the observational capability to catch up. And catch up it did, through the sustained engineering effort that produced instruments like ASKAP, an array designed from the ground up to have an exceptionally wide field of view, allowing it to monitor large areas of sky simultaneously and dramatically increasing the probability of catching a fast radio burst in real time rather than discovering it only in archival data after the fact, and through the development of computational pipelines capable of processing the enormous data streams produced by these instruments quickly enough to identify a transient event within seconds of its arrival, before the signal has faded and before the precise pointing information needed for localization has been lost. The detection of FRB Arsenling Ling Lubaik Isha A happened in real time. Flagged automatically by ASKAP's onboard systems, and the data were preserved with sufficient fidelity to allow the full interferometric analysis needed to pinpoint the burst's position in the sky to within arcseconds. That this is now possible, that the infrastructure exists to catch a millisecond pulse from billion light-years away, identify it as it arrives, and trace it back to its home galaxy within the noise of the deep-field sky is a testament to what patient, cumulative, collaborative science can achieve across decades of work by generations of researchers, who may never have met each other but who were all, in their own ways, building toward the same horizon. The broader context in which FRB Arsenling Lubai Ishur A exists is one of accelerating discovery, in which the pace of detection and localization of fast radio bursts is increasing faster than many in the field had anticipated even a few years ago. The KIME telescope, which came to full operation in Arsenling Sabah, has been particularly transformative in this regard, having detected and catalogued more fast radio bursts in its first few years of operation than all previous instruments combined. KIME's design, a set of 4 semi-cylindrical reflectors, each 100 meters long and 20 meters wide, fixed to the ground and scanning the sky as Earth rotates, with no moving parts and a field of view covering a large fraction of the northern sky at any given moment, makes it extraordinarily efficient at catching transient events, though its fixed design and relatively short baselines limit its ability to localize individual bursts with the arcsecond precision achieved by ASKAP's interferometric mode. The two instruments are in many ways complementary. CHIME provides volume and statistics, cataloging hundreds of bursts and revealing the population-level properties of the FRB phenomenon, while ASKAP provides precision, localizing individual bursts to specific host galaxies and enabling the detailed follow-up observations that extract the deepest cosmological information. Together, they represent two facets of a growing global effort to understand fast radio bursts, an effort that also includes instruments like Macquart in South Africa, the 500-meter aperture spherical radio telescope in China, the upgraded giant Metro-Wave radio telescope in India, the Deep Synoptic Array in California, and the European VLBI network, a constellation of radio observatories spread across multiple continents, or contributing their unique capabilities to the collective project of mapping the radio transient universe and decoding the messages that arrive from its most extreme and energetic corners. There is a particular kind of scientific beauty in the idea that the universe has been sending us messages across billions of years, and that we have only recently, in the last few decades of a civilization that has existed for a few thousand years on a planet that has existed for 4.5 billion, developed the sensitivity and sophistication to receive them. Fast radio bursts are, in this sense, a kind of cosmic correspondence that has been accumulating in the universe's outbox for an eternity, waiting for a recipient capable of recognizing the signal for what it is. And what it is, at its most fundamental, is information, raw, unfiltered information about the state of the universe across enormous spans of time and space, encoded not in any language we invented, but in the language of physics itself, in the dispersion of radio waves through plasma, in the redshift of wavelengths stretched by cosmic expansion, in the polarization of electromagnetic radiation twisted by magnetic fields encountered along the journey. Learning to read this information is one of the great intellectual projects of our era, and it is a project that connects the most abstract reaches of theoretical cosmology to the most concrete and practical challenges of telescope engineering, signal processing. It is a project that requires both the mathematician and the machinist, both the theorist sketching equations on a whiteboard and the engineer soldering connections in an antenna assembly on a windswept Australian plain, and it is the collaboration between these different kinds of minds, working across different institutions and different countries and different scientific traditions, that has brought us to the point where a signal from billion light-years away can be not merely detected but understood, not merely registered but interpreted, not merely seen but read. To read the signal of FRB, R10 Ling Arsher R Wen Ling Lupek Isher A fully, astronomers needed to do more than measure its dispersion. They needed to understand its polarization, the orientation of the electromagnetic wave's oscillation as it traveled through space, because polarization carries its own set of messages about the environments the signal traversed. Radio waves can be linearly polarized, meaning that their electric field oscillates in a single plane, or circularly polarized, meaning that the electric field rotates as the wave propagates, or some combination of both. When a linearly polarized radio wave passes through a region of magnetized plasma, The plane of its polarization rotates by an amount that depends on both the strength of the dot magnetic field and the density of electrons in the plasma, an effect known as Faraday rotation, named for the 19th century English scientist Michael Faraday, whose experiments with electricity and dot magnetism laid the groundwork for much of what we now understand about electromagnetism. By measuring the rotation measure of a fast radio burst, the degree to which its dot polarization plane has been rotated during its journey, astronomers gain access to information about the magnetic fields threaded through the ionized gas along the line of sight, adding another dimension to the picture of intergalactic space that the dispersion measure alone cannot provide. Magnetic fields in the intergalactic medium are extremely weak by any terrestrial standard, many orders of magnitude weaker than the field of a refrigerator magnet, yet they are present and they are cosmologically significant, shaping the flow of cosmic rays, influencing the structure of galaxy clusters, and potentially playing a role in the large-scale evolution of cosmic structure that is still not fully understood. Fast radio bursts, with their measurable rotation measures, offer a new way to probe these invisible magnetic architectures woven through the fabric of the cosmic web, and the rotation measure of FRB, R10 Ling, R1 Ling Lobar Isha A added one more data point to the slowly growing map of intergalactic magnetic fields that astronomers are patiently assembling from the ensemble of localized bursts. The polarization properties of fast radio bursts more broadly have revealed something else of considerable scientific interest, a diversity that hints at the complexity of the environments immediately surrounding the sources themselves. Some fast radio bursts show nearly 100% linear polarization, 100%. A herd per stick, suggesting that they are produced by a highly coherent emission mechanism operating in a relatively clean environment. Others show more complex, with the degree and angle of polarization varying across the frequency band of the signal in ways that suggest passage through turbulent or inhomogeneous magnetic environments close to the source. Some repeating fast radio bursts have shown dramatic changes in their rotation measures between successive bursts from the same location, implying that the magnetized plasma immediately surrounding the source is dynamic and evolving on timescales of days to months. One particularly well-studied repeating source, FRB, Arsene Ling Ishira Wan Ichen Ebyte Ling Ra, the first fast radio burst ever confirmed to repeat, localized to a dwarf galaxy approximately 3 billion light-years away and embedded within an extraordinarily dense and magnetized environment, showed rotation measures hundreds of times larger than those typical of other bursts, suggesting that it resides within or very near an extremely dense magnetized nebula, possibly the remnant of the supernova that created the magnetar responsible for the bursts, or a nebula powered by the magnetar's own wind of energetic particles. The diversity of these environments, reflected in the diversity of polarization properties across the FRB catalog, reinforces the view that while magnetars may be the engines of fast radio bursts as a class, the specific characteristics of individual bursts are shaped by the particular circumstances of their immediate surroundings in ways that are still being mapped and understood. There is a thread running through all of this that connects the microscopic physics of a neutron star's interior to the macroscopic architecture of the universe itself. And following that thread from one end to the other is an exercise in the kind of vertigo-inducing scale crossing that makes astrophysics unlike any other science. Consider what is happening at the moment of a fast radio burst, in the milliseconds during which the signal is generated. Inside a magnetar, an object 20 kilometers across, less than the distance across a medium-sized city. The crust, a layer of crystallized nuclear matter only a kilometer or so thick, experiences a sudden fracture. The trigger for this fracture is the enormous stress imposed on the crust by the magnetar's own magnetic field, which has become so intense and so twisted by the neutron star's rotation and by internal fluid motions that it exerts a force the solid crust can no longer resist. The crack propagates through the crust in a fraction of a second, releasing stored magnetic energy in a cascade that drives currents of charged particles along the magnetic field lines extending from the star's surface out into the surrounding magnetosphere. These particles, accelerated to relativistic velocities along curved magnetic field lines, emit radiation through a process of coherent curvature emission, a mechanism related to but more efficient than the synchrotron radiation that produces the radio emission of ordinary pulsars, and the result is a coherent burst of radio waves with a luminosity that, for its brief duration, exceeds that of entire galaxies. This is the physics of the source: nuclear material fracturing under magnetic stress, relativistic particles screaming along magnetic field lines, coherent radio emission blazing outward in a beam or a fan pattern, depending on the geometry of the magnetosphere, all happening in a space smaller than a city, all over in less time than it takes to draw a breath. And then that burst of radio waves begins its journey, a billion light years of expanding space, billion years of cosmic time, a journey that will carry it through the magnetar's host galaxy, through the intergalactic medium, through the large-scale structures of the cosmic web, through the local group of galaxies, through the thin halo of gas surrounding the Milky Way, and finally down through the atmosphere of a small blue planet orbiting an unremarkable star in one of the Milky Way's spiral arms, where 36 parabolic dishes are waiting in the desert pointed at the sky, listening. The listening is itself an act of extraordinary technical precision, and the systems that make it possible deserve more than passing acknowledgment, because they represent a kind of human ingenuity applied to the challenge of cosmic listening. That is every bit as remarkable as the cosmic events being listened for. The ASKAP telescope, the Australian Square Kilometre Array Pathfinder, was designed specifically with wide-field radio transient detection in mind, and its most distinctive technical feature is the phased array feed installed at the focus of each of its 36 12-meter dish antennas. Unlike conventional radio telescope receivers, which collect radiation from a single point on the sky at any given moment, phased array feeds use an array of individual receiving elements whose signals can be combined electronically to form multiple simultaneous beams, each pointed at a slightly different region of the sky. ASKAP's phased array feeds can produce up to 36 simultaneous beams per dish, and when all 36 dishes are combined in their standard survey mode, the telescope can monitor a region of sky roughly 30 square degrees in area, a patch roughly 60 times the size of the full moon, with a sensitivity sufficient to detect fast radio bursts from cosmological distances. This wide-field temperature detection machine, CP Shores, and CP1's capability. This wide-field capability is what makes ASKAP so effective as an FRB detection machine, where a conventional single-dish telescope might catch a fast radio burst only by chance, when its narrow beam happened to be pointed in the right direction at the right moment. ASKAP systematically surveys large areas of sky, vastly increasing the probability of catching a burst in any given observing session. The detection of FRB, Arsenling Arsar Wenling Lupite Isher A, was not a stroke of luck. It was the predictable outcome of a well-designed survey strategy executed with sophisticated instrumentation, the kind of result that emerges when scientific vision and engineering excellence are aligned toward a clear observational goal. Once a burst is detected by ASKAP's automated systems, flagged in real time by algorithms scanning the incoming data, stream for the characteristic dispersion signature of an extragalactic radio pulse, the data from all 36 antennas are preserved and combined to perform the interferometric analysis that yields the precise sky position of the source. This involves measuring, with nanosecond precision, the tiny differences in arrival time of the burst signal at each antenna, and using those time differences to calculate the direction from which the signal arrived through a process of geometric triangulation that, in its mathematical, is not so different from the triangulation a surveyor uses to determine the position of a distant point on Earth's surface, though the scales and the required precision are of a different order entirely. The result of this analysis for FRB, Arsien Ling Arsara Wan Ling Lobak Isha A, was a position accurate to approximately 1 arcsecond, 1/3600th of a degree, precise enough to identify, in optical images of the corresponding region of sky, a single faint galaxy as the most likely host, ruling out all other objects in the field as possible sources of the burst. Lexi subsequently observed in detail with the Very Large Telescope's Muse spectrograph, an instrument capable of obtaining a spectrum at every point across an extended field of view simultaneously, was confirmed to lie at a redshift consistent with the distance inferred from the burst's dispersion measure. Closing the observational loop and establishing FRB, Arsen Ling Arsa Arwan Ling Lupide Isha A, as a new landmark in the expanding catalogue of precisely localized fast radio bursts from cosmological distances. The Very Large Telescope's contribution to this discovery is a reminder that fast radio burst science, despite its radio wave origin, is fundamentally a multi-wavelength enterprise, that the full story of any individual burst can only be told by combining radio observations with optical and sometimes infrared and X-ray data, each wavelength regime contributing information that the others cannot provide. The radio observations tell us about the signal itself, its dispersion, its polarization, its duration and frequency structure, the information it carries about the intergalactic medium. The optical observations tell us about the host galaxy, its stellar mass, its star formation rate, its metallicity, its morphology, its environment, providing the astrophysical context needed to understand what kind of source is likely to reside there. And what conditions might have led to the production of a burst of this particular energy and character. Together, these complementary datasets build a picture that is richer and more informative than either could provide alone, a picture that speaks not only to the specific event of FRB, Arsenling Arshar Wen Ling Lubai Isher A, but to the broader questions of how fast radio bursts form, what they can tell us about the universe's matter distribution, and how they fit into the larger story of cosmic evolution across billions of years of time. There is a question that sits quietly beneath all of the technical achievement and observational triumph. Described so far, a question that does not announce itself loudly, but that becomes impossible to ignore once you have spent enough time thinking about what fast radio bursts are, where they come from, and what they can tell us about the universe. The question is this: What does it mean that the universe is structured in such a way that a millisecond event in a distant galaxy, an event so brief and so localized that it occupies an infinitesimally small fraction of cosmic space and time, can carry within it information about the entire column of matter between its source and our instruments across billion light-years of space? What does it mean that the universe is, in some deep sense, legible? That its large-scale structure, its matter distribution, its magnetic architecture, its expansion history are all encoded in the properties of signals that cross it, and that patient and clever observation can decode those encodings and extract from them a picture of the cosmos that no other technique can provide with equal directness? This is not a mystical question, though it edges toward territory that philosophers of science have long found interesting. It is, at its core, a question about the nature of physical law and the remarkable fact that the same laws of electromagnetism, the same equations that describe how radio waves interact with free electrons in a laboratory on Earth, apply without modification across the entire observable universe, at every distance and every epoch that astronomical observation has yet reached. This universality of physical law is so familiar to working scientists that it can become invisible, taken for granted, assumed without comment, but it is, when examined directly, one of the most profound and least explained features of the physical world, and it is the foundation upon which all of cosmological observation rests. The universality of physical law is what makes the Macquart Relation work. It is what makes the dispersion measure of a fast radio burst a trustworthy probe of intergalactic electron density rather than an artifact of local conditions or a reflection of some exotic physics operative only near the source. It is what allows astronomers to take the dispersion measure of FRB, Arsen Ling Arsara Wan Ling Lu Bide Isha A number derived from timing differences measured in nanoseconds across an array of radio antennas in the Australian desert, and translate it, through a chain of well-tested physical reasoning, into a statement about the average density of ordinary matter in the intergalactic medium across half the observable universe. The chain of reasoning is long, and every link in it depends on the assumption that the same physics applies throughout, that electrons in intergalactic space billion light-years away interact with radio waves in exactly the same way that electrons in the interstellar medium of the Milky Way do, that the expansion of the universe follows the same general relativistic equations at every point and every epoch, that the atomic and nuclear physics governing the behavior of matter in lots, neutron stars and plasma clouds is the same everywhere and always. These are assumptions that have been tested in many ways, and in many contexts, and have never been found to fail, but they are assumptions nonetheless. And part of what makes each new observation at the frontier of distance and time valuable is that it provides yet another test of these foundational assumptions, another opportunity for the universe to reveal, if it were inclined to, some deviation from the laws we have derived from observations much closer to home. So far, the universe has declined to reveal any such deviation. The laws hold, the physics is universal, and that universality is what allows a signal from a billion light-minus years away to be not merely a curiosity, but a scientific instrument. The cosmological implications of this extend well beyond the specific question of missing baryons, important as that question is. Fast radio bursts, as their catalog grows and as the precision of their localizations improves, are beginning to be recognized as potential probes of a much wider range of cosmological phenomena, some of which touch on the deepest and most unresolved questions in all of physics. One of the most tantalizing of these applications involves the measurement of the Hubble constant, the rate at which the universe is currently expanding, which has in recent years become one of the most contentious topics in cosmology, the site of a genuine and significant disagreement between different measurement methods that has come to be known as the Hubble tension. The Hubble constant, denoted h-ractude, can be measured in two fundamentally different ways: by observing the local universe, using the distances and recession velocities of nearby galaxies calibrated through a chain of distance indicators known as the cosmic distance ladder, and by observing using the precise pattern of temperature fluctuations in the cosmic microwave background to infer the expansion rate through the lens of the standard cosmological model. The problem, the tension, is that these two methods give different answers. Local measurements consistently find a Hubble constant of around 36 kilometers per second per megaparsec, while measurements based on the cosmic microwave background yield a value closer to t kilometers per second per megaparsec. The discrepancy is small in absolute terms but large in statistical significance. Several standard deviations, enough to be taken seriously as a potential indicator that something in our standard cosmological model is missing or wrong, though not yet large enough to definitively rule out the possibility that it reflects uncharacterized systematic errors in one or both measurement chains, rather than new physics. Fast radio bursts offer a potential third way to measure the Hubble constant, independent of both the cosmic distance ladder and the cosmic microwave background, by exploiting the relationship between dispersion measure and distance in a statistical ensemble of localized bursts. The method is not yet precise enough to resolve the tension on its own, but as the number of precisely localized bursts grows from the current dozens into juice, the hundreds and eventually thousands that next-generation instruments are expected to provide, the statistical power of this approach will increase, and fast radio bursts may eventually contribute a genuinely independent measurement of h-pseudot that helps clarify whether the Hubble tension represents a systematic error or a genuine crack in the foundations of the standard cosmological model. The possibility that the Hubble tension might be pointing toward new physics, toward some modification or extension of the standard lambda CDM cosmological model that has dominated cosmology for the past few decades, is one that the community takes seriously without yet embracing. Maintaining that careful balance between openness to new ideas and rigor in evaluating evidence that defines good science. Lambda CDM, as it is known, is a model in which the universe contains three primary components: ordinary baryonic matter, making up only about 5% of the total energy density, called dark matter; an invisible and still unidentified form of matter that interacts gravitationally but not electromagnetically and accounts for roughly 27% of the total; and dark energy, represented by the cosmological constant lambda in Einstein's equations, a form of energy associated with empty space itself that drives the accelerating expansion of the universe and makes up the remaining 68% of the total energy density. This model accounts with remarkable precision for an enormous range of observations: the clustering of galaxies, the abundance of galaxy clusters, the baryon acoustic oscillation signal in the distribution of galaxies, the detailed pattern of the cosmic microwave background, and it is by far the most successful and well-tested framework for understanding the universe's large-scale structure and evolution. Yet it is a model built on two completely mysterious foundations: dark matter and dark energy, whose physical nature remains entirely unknown despite decades of experimental and theoretical effort. Fast radio bursts, interestingly, may be able to probe aspects of both of these mysteries in ways that are still being explored. The dispersion of fast radio bursts through the intergalactic medium is sensitive to the distribution of baryonic matter, but the overall relationship between dispersion measure and redshift also depends on the cosmological model, on the values of the dark matter density, the dark energy density, and the Hubble constant, meaning that a sufficiently large ensemble of precisely localized bursts can, in principle, constrain these cosmological parameters and test the lambda CDM model in a regime, the universe's matter distribution at intermediate redshifts, that is complementary to other observational probes. This vision of fast radio bursts as precision cosmological instruments is still largely prospective, a program for the future rather than a fully realized achievement of the present. But it is a vision grounded in demonstrated capability rather than mere aspiration, and the detection of FRB Arsène Ling R1 Ling Loop Isha A at redshift 1 is a concrete step toward its realization. Every localized burst at cosmological distance is a calibration point for the Macquart Relation, a test of the relationship between dispersion measure and distance that the cosmological probe program depends upon, and a demonstration that the technical infrastructure for detecting and localizing bursts at these distances is operational and improving. The scientific community is, in this sense, in the early stages of building a new kind of observatory, not a physical instrument in any single location, but a distributed, global, multi-wavelength network of detection and follow-up capabilities connected by data sharing agreements and coordinated observation strategies, whose collective output will be a census of fast radio bursts across the observable universe comprehensive enough to serve as the foundation for precision cosmological measurements. This is ambitious, and it will take years, possibly decades, to fully realize. But the trajectory is clear and the pace of progress is accelerating. Meanwhile, as the cosmological applications of fast radio bursts develop, the more immediate and equally fundamental question of what actually produces them continues to attract intense theoretical and observational attention. The magnetar hypothesis, as we have discussed, is supported by direct observational evidence from the galactic burst associated with SGR. Isen Jubite Sansawu, Nisen Ebike Wushasu, and it provides a plausible physical mechanism for the energy release required. But the diversity of the fast radio burst population, the existence of repeating and apparently non-repeating bursts, the range of energy spanning several orders of magnitude, the variety of spectral and polarization properties, the different host galaxy environments, raises the question of whether the magnetar model is truly a single unified explanation, or whether it is rather a category within which significant diversity exists, or perhaps a framework that encompasses some but not all fast radio burst sources. There are theorists who argue that certain categories of fast radio bursts, particularly those at the most extreme end of the energy distribution, and FRB, Arsène Ling Arsa R1 Ling Loopback Isha A, with its exceptional luminosity is relevant here, may require the involvement of binary systems, in which a magnetar or pulsar interacts with a companion star or compact object, in ways that produce more energetic events than a solitary magnetar could achieve. Others have proposed that the coalescence of binary neutron star systems, events of the same general class as the merger detected in gravitational waves by LIGO and Virgo in August, Ertenling ESHT, designated GW 11817, and accompanied by a short gamma-ray burst, might produce fast radio bursts in their final moments before merger, or in the aftermath of the merger if the resulting remnant is a magnetar rather than a black hole. These models are not mutually exclusive, and the history of gamma-ray burst research, which eventually revealed that what appeared to be a single class of events was in fact two distinct populations with different progenitors, long gamma-ray bursts associated with the collapse of massive stars and short gamma-ray bursts associated with compact object mergers, suggests that intellectual humility about the unity of the fast radio burst class is warranted. What the ensemble of current evidence most strongly suggests is that the universe is, as it so often turns out to be when examined closely enough, more complex and more interesting than our initial models assumed. The fast radio burst phenomenon, rather than being a single well-defined event with a single well-defined progenitor, appears to be a label that encompasses a range of related but potentially distinct physical processes, all of which share the common feature of producing coherent, brief, and extremely luminous radio emission from compact objects at cosmological distances, but which may differ in their detailed physical mechanisms, their progenitor populations, their host galaxy preferences, and their statistical properties in ways that will only become fully apparent as the catalog grows and the analysis deepens. This complexity is not a problem for the field. It is an opportunity, a sign that the fast radio burst window onto the universe is broader and richer than the simplest initial models suggested, and that the scientific harvest to be gathered from it will be correspondingly greater. The signal from a billion light-years is not just one message. It is part of a conversation that the universe has been conducting with itself across its entire history, a conversation written in radio waves and magnetic fields, and the dispersion of electrons through vast reaches of intergalactic space, and we are only just beginning to learn enough of the language to follow along, to follow that conversation more deeply, to trace the thread of what fast radio bursts are telling us about the universe. Large-scale structure and matter distribution with the patience and care the subject deserves, we must spend some time with the cosmic web itself, that extraordinary architecture of filaments, sheets, nodes, and voids that constitutes the universe's largest and most fundamental organizational structure. The scaffolding upon which every galaxy cluster, every quasar, and every star ultimately hangs. The cosmic web is not a metaphor, and it is not a theoretical construct imposed upon the data by cosmologists seeking patterns where none exist. It is a real and observable feature of the universe, visible in the three-dimensional maps of galaxy positions assembled by large redshift surveys like the Sloan Digital Sky Survey, which over 2 decades of operation mapped the positions and redshifts of hundreds of millions of galaxies and revealed with unmistakable clarity the filamentary, web-like distribution of matter on scales of hundreds of millions of light-years. The web consists of dense filaments of dark matter and gas connecting massive galaxy clusters at their nodes, sheets of intermediate density separating the filaments, and vast voids, regions of space tens to hundreds of millions of light-years across, that contain almost no galaxies and almost no ordinary matter, filling the spaces between. Is not random. It is the gravitational legacy of tiny quantum fluctuations in the density of the early universe. Fluctuations that existed in the first moments after the Big Bang were amplified by inflation to cosmological scales and then grew under gravity over billions of years from nearly imperceptible ripples in the density field to the dramatic mountains and valleys of the cosmic web we observe today. understanding the cosmic web, its geometry, its matter content, its magnetic field structure, its evolution over cosmic time, is central to understanding the universe itself, and it is here that fast radio bursts are making some of their most significant and most irreplaceable contributions. The connection between fast radio bursts and the cosmic web is mediated by the same physical process that makes FRB's useful cosmological probes in general, the dispersion of radio waves by free electrons. But in this context, the focus shifts from the average electron density along a line of sight to the variations in that density, the fluctuations that reflect the web's filamentary structure. When a fast radio burst travels from its source to our instruments, it does not pass through a perfectly uniform distribution of electrons. It passes through a structured medium, encountering filaments of higher density where the cosmic web's threads concentrate gas, crossing voids where the electron density drops to almost nothing, and threading through the circumgalactic medium, the extended halo of gas surrounding individual galaxies at various points along its path depending on the geometry of the line of sight. Each of these encounters leaves a small imprint on the burst's dispersion measure, adding or subtracting from the total in a way that depends on the specific path the burst took through the web's complex three-dimensional structure. Individual burst. This path dependence introduces an uncertainty, a scatter in the dispersion measure that cannot be attributed to the smooth average described by the Macquart Relation, but instead reflects the particular cosmic web environment that specific burst happened to traverse. This scatter is not merely a source of noise to be minimized. It is itself a signal carrying information about the statistical properties of the cosmic web's matter distribution, its clumpiness, its filament widths, its void sizes that can be extracted through the analysis of large samples of bursts from similar redshifts. The scatter in the dispersion measure redshift relation, carefully measured across an ensemble of localized fast radio bursts, becomes a probe of cosmic web structure, complementing the galaxy surveys that map the web's luminous components with a measurement of the web's total baryonic content, including its invisible diffuse gas. This approach has already begun to yield results, though the sample sizes currently available limit the precision of the constraints. The analysis of the first few tens of precisely localized fast radio bursts showed a scatter in the dispersion measure redshift relation that is broadly consistent with predictions from cosmological simulations of the cosmic web, suggesting that the simulations are capturing the essential features of the web's gas distribution, even if the detailed physics of feedback from galaxies and active galactic nuclei the processes by which energy injected into the intergalactic medium by star formation, stellar winds, and supermassive black hole activity redistributes gas on large scales, remains uncertain and actively debated. As the sample of localized bursts grows, the precision of these constraints will improve, and fast radio bursts may eventually be able to distinguish between different models of how galactic feedback processes shape the distribution of gas in and around the cosmic web's filaments, a question of considerable importance for understanding how galaxies form and evolve within the larger context of cosmic structure. The connection between the small scale, the galaxy with its supermassive black hole and its stellar populations and its outflowing winds, and the large scale, the cosmic web with its filament spanning hundreds of millions of light years, is one of the central problems in modern astrophysics, and the fact that fast radio bursts can probe it from the outside by measuring the integrated effect of all of this gas physics along the line of sight across cosmological distances makes them a uniquely powerful complement to the detailed but necessarily local observations that other techniques provide. One of the most striking illustrations of this complementarity came from a study published in Arsenling Arsersan shortly before the announcement of FRB, Arsenling Arwenling Loopback Isher A, in which a team of astronomers used a sample of localized fast radio bursts to probe the gas content of the halos surrounding foreground galaxies that happen to lie along the lines of sight to the bursts. When a fast radio burst's path passes close to a foreground galaxy, close in projection on the sky, not in physical space, the burst signal passes through the circumgalactic medium of that galaxy, the diffuse and extended atmosphere of gas that surrounds galaxies far beyond their visible stellar bodies, sometimes extending for hundreds of thousands of light years in all directions. This circumgalactic medium is one of the most important and least understood components of the galactic ecosystem. It is the reservoir from which galaxies draw the gas needed to fuel star formation, the repository into which galactic winds eject material enriched with heavy elements forged in stellar interiors, the boundary layer between the galaxy and the intergalactic medium, through which the exchange of matter and energy between these two regimes takes place. Direct observation of the circumgalactic medium is challenging because it is diffuse, extended, and composed largely of gas at temperatures and densities that produce relatively faint emission or absorption signals, requiring extremely sensitive instruments and long observation times to detect. But a fast radio burst passing through it experiences an excess dispersion, a contribution to the total dispersion measure over and above what would be expected from the smooth intergalactic medium alone, that can be measured and attributed to the foreground galaxy's halo gas. By stacking the dispersion measures of many fast radio bursts whose lines of sight pass near many foreground galaxies and analyzing the statistical excess as a function of impact parameter, the angular separation between the burst's line of sight and the center of the foreground galaxy, astronomers can reconstruct the average radial profile of gas in galactic halos, measuring how the electron density of the circumgalactic medium varies with distance from the galaxy center, in a way that has not previously been achievable through any other technique at cosmological distances. This application of fast radio bursts to circumgalactic medium science is still in its early stages, but it is already producing results that are consistent with and complementary to other probes of galactic gas halos, and it represents another dimension of the broad scientific program that the growing FRB catalog is enabling. The circumgalactic medium studies connect fast radio bursts to one of the most actively debated topics in galaxy formation theory, a question of how galaxies regulate their own growth. Why star formation in massive galaxies appears to have shut down billions of years ago, while lower mass galaxies continue to form stars at measurable rates today, and what role the circumgalactic medium plays in mediating this regulation by controlling the supply of cold gas available to fuel star formation. These questions are deeply connected to the physics of feedback, the processes by which energy output from star formation and from the supermassive black holes at galaxy centers couples to the surrounding gas and drives outflows, heats the circumgalactic medium, and prevents the accretion of new gas onto the galaxy. The details of feedback physics are notoriously difficult to observe directly and notoriously uncertain in the simulations used to model galaxy formation, with different simulation codes making different assumptions about how feedback energy is injected and distributed, and producing somewhat different predictions for the resulting gas distributions in and around galaxies. Fast radio bursts, by providing observational constraints on the actual gas content of galactic halos across a range of galaxy masses and redshifts, offer a way to test these predictions and discriminate between models, a prospect that is generating considerable excitement among both the fast radio burst community and the galaxy formation community, and that is driving collaborative efforts to design observation strategies optimized for circumgalactic medium science using future, larger FRB samples. Stepping back from these specific applications to the broader landscape of what FRB science is revealing, it becomes apparent that we are witnessing the emergence of a genuinely new branch of observational astronomy, one that did not exist as a coherent discipline 20 years ago, that barely existed as a recognizable field 15 years ago, and that is now expanding rapidly in both its observational scope and its theoretical depth. This emergence is driven partly by the development of new instruments with the capabilities needed to detect and localize fast radio bursts at cosmological distances, but it is driven equally by a growing recognition within the broader astronomical community that the universe is radio transient sky. The landscape of brief, energetic variable radio phenomena is far richer and more scientifically productive than was appreciated before the FRB era began. The discovery that the sky is filled with fast radio bursts arriving from all directions and all distances has changed the way astronomers think about the radio sky more broadly, prompting new searches for other kinds of radio transients, new designs on wide-field radio monitoring systems, and new theoretical frameworks for understanding the range of physical processes that can produce coherent radio emission from compact objects. In this sense, the signal from billion light-years is not just a single discovery, it is a marker of a transformation in how we observe and understand the dynamic universe, a universe that is not the static and slowly evolving place that early astronomy depicted, but a restless, continuously active cosmos in which catastrophic events occur constantly, in which energy is released and information is broadcast across cosmological distances on timescales ranging from milliseconds to billions of years, and in which our instruments, if we design them with sufficient ambition and build them with sufficient care, can intercept and decode those broadcasts and extract from them a progressively deeper and more complete picture of the physical world we inhabit. The Square Kilometre Array, the SKA, represents the most ambitious expression of that ambition currently under construction, a radio telescope array whose planned sensitivity and survey speed will dwarf all previous instruments. And whose contribution to fast radio burst science is anticipated to be transformative. The SKA is being built in two phases, with SKA Low, consisting of hundreds of thousands of simple dipole antennas spread across a large area of Western Australia sensitive to low radio frequencies, and SKA Mid, consisting of hundreds of dish antennas in South Africa sensitive to higher frequencies, together forming a system whose total collecting area will be measured in square kilometers, hence the name, and whose sensitivity will be sufficient to detect fast radio bursts at redshifts far greater than any currently achieved, potentially reaching sources in the first few billion years of cosmic history, when the universe was young and star formation was at its most intense. The prospect of detecting and localizing fast radio bursts at redshifts of 2, 3, 4, or beyond, in a universe less than half, less than a quarter, less than a sixth of its current age, opens windows onto cosmic epochs that are currently accessible only through the most powerful observations of the most luminous and extreme objects, quasars and gamma-ray bursts and gravitational wave sources, and it raises the tantalizing possibility of using fast radio bursts to probe the reionization epoch itself, the period in the universe's first billion years when the first stars and galaxies lit up and their radiation ionized the neutral hydrogen that had filled the cosmos since recombination. The dispersion measure of a fast radio burst from the epoch of reionization would carry within it a record of how and when that ionization occurred, information of fundamental importance for understanding the universe's transition from its dark ages to its current luminous state, and detecting such a burst would represent one of the most significant observational achievements in the history of cosmology. The epoch of reionization is one of the great frontiers of modern cosmology, a period so remote in time and so difficult to observe directly that it has until recently existed, primarily as a theoretical construct, a chapter in the universe's story that we knew must have happened, whose broad outlines we could infer from indirect evidence, but whose details remain shrouded in a darkness that our best instruments had not yet penetrated with sufficient clarity to resolve. To understand why this epoch is so important, and why the prospect of using fast radio bursts to probe it generates such genuine excitement among cosmologists, we must first understand what the universe was like before reionization occurred, what the cosmos looked like in the long and quiet interval between the formation of the first neutral atoms and the ignition of the first stars, a period that astronomers have given the evocative name of the cosmic dark ages. This name is not merely poetic. It describes a real and fundamental feature of the early universe, a time when the cosmos contained no sources of light, when the only matter present was the primordial hydrogen and helium produced in the first minutes after the Big Bang, along with the invisible dark matter that was already beginning to clump under gravity, when the universe was filled with a neutral gas that was, from the perspective of any hypothetical observer, truly and completely dark. No stars burned, no galaxies shone, no quasars blazed at the centers of forming galaxy clusters. The universe existed in a state of quiet, cold, expanding darkness, punctuated only by the faint microwave glow of the cosmic background radiation left over from the earlier epoch of recombination, the moment, roughly some bashing years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, and the cosmos became transparent to light for the first time. That microwave glow, the cosmic microwave background, we can still detect today with our most sensitive instruments, and it is one of our most powerful sources of information about the early universe. But between the epoch of recombination and the epoch of reionization, there is a gap, a dark interval of perhaps several 100 million years that has been extraordinarily difficult to observe directly, because the neutral hydrogen that filled the universe during this period absorbed Tavanri Trinitefestis, almost all radiation at the wavelengths most useful for probing it, creating an effective opacity that blocks our view of this cosmic chapter. Read Shreep or worries. Wake. Worries. Low as surely as a thick fog blocks the view of a distant landscape. Nation ended the Dark Ages. It was the process by which the ultraviolet radiation from the first generations of stars, and subsequently from the first quasars and active galactic nuclei, stripped the electrons from the neutral hydrogen atoms that filled the intergalactic medium, converting it from a neutral gas to an ionized plasma and making the universe transparent to ultraviolet light. This was not a sudden, instantaneous transition, but a gradual and patchy process that unfolded over hundreds of millions of years, beginning perhaps Ebak Wushers 2 Urbak million years after the Big Bang with the formation of the first stars, the so-called population 3 stars, formed from pure hydrogen and helium with no heavier elements, and predicted by theory to have been enormously massive and intensely luminous, and completing somewhere around 1 billion years after the Big Bang, when the ionizing radiation from the growing population of stars and quasars had finally permeated every corner of the intergalactic medium and the last pockets of neutral hydrogen had been consumed. The details of this process, how it began, how quickly it progressed, whether it was driven primarily by stars or by quasars, how the ionization fronts propagated through the neutral gas, what the topology of the ionized bubbles looked like at various stages, are questions. Concepts of fundamental importance for understanding how the universe's first structures formed and evolved, and they remain subjects of active theoretical debate and intensive observational effort. The James Webb Space Telescope, launched in December, now delivering data of breathtaking quality from its orbit around the Sun-Earth LR point, is contributing enormously to the study of the reionization epoch by detecting galaxies in the first few 100 million years of cosmic history with a sensitivity and resolution that no previous instrument could achieve, revealing a population of early galaxies that are, in some respects, surprisingly mature and well-organized for objects that formed so early in cosmic time, a finding that has already prompted some revisions to theoretical models of early galaxy formation, and that continues to generate productive scientific debate. Fast radio bursts, in the context of the reionization epoch, offer a complementary and in some ways uniquely powerful probe, precisely because their dispersion measures integrate the electron density along the entire line of sight. From source to observer, including any neutral hydrogen that has been ionized along the path. A fast radio burst originating from a source within or just beyond the reionization epoch would carry within its dispersion measure a contribution from the reionized intergalactic medium of the early universe, and the magnitude of that contribution would depend on how much of the intergalactic medium had been ionized by the time the burst was emitted and how that ionization was distributed along the line of sight. By detecting fast radio bursts at a range of redshifts spanning the reionization epoch and measuring how their dispersion measures evolve with redshift in the region where reionization is occurring, astronomers could in principle map the progress of reionization in a way that is direct, quantitative, and independent of the galaxy observations and quasar absorption spectra that currently provide most of our information about this epoch. The challenge, of course, is detecting fast radio bursts at such extreme distances, at redshifts of 6, 7, 8, or beyond, corresponding to times when the universe was less than 1 billion years old. Because the sensitivity required to detect a millisecond pulse from such a distance, even from a source as intrinsically luminous as the most energetic fast radio bursts known, pushes well beyond the capabilities of current instruments and into the domain of what the square kilometer array and its successors may eventually achieve. But the scientific return on this investment, if it can be realized, would be extraordinary, a direct measurement of the reionization history of the universe encoded in the dispersion measures of ancient radio pulses, a new chapter in the story of how the cosmos emerged. from its dark ages into the luminous epoch we now inhabit. In the meantime, the fast radio bursts we can currently detect, at redshifts up to and now beyond 1, in a universe between half and 2/3 of its current age, are providing a picture of the neat universe's matter distribution at intermediate cosmic epochs that is already scientifically rich and that is beginning to reveal features of the cosmic web and the intergalactic medium that were not previously accessible. One of the most significant of these features is the distribution of gas between galaxies, not the gas within galaxies or in galaxy clusters, which is relatively well characterized by X-ray observations and optical spectroscopy, but the gas in the true intergalactic voids and in the moderate minus density filaments that connect galaxies to one another across the cosmic web. This gas, the warm-hot intergalactic medium, or WHM, that we encountered in the opening chapters of this story, exists at temperatures between 100,000 and 10 million Kelvin, heated by the gravitational shock heating that occurs as matter falls into the cosmic web's filaments, and by the feedback energy injected into the intergalactic medium by star formation and active galactic nuclei over cosmic time. At these temperatures, the gas is too hot to produce the cold hydrogen emission detected by radio telescopes in the Ursa centimeter line, too diffuse to produce strong X-ray emission detectable by current X-ray satellites, and too highly ionized to produce the UV absorption lines that quasar spectroscopy uses to trace cooler intergalactic gas. It is, in almost every observational sense, nearly invisible, present in the simulations, predicted by the theory, demanded by the baryon budget, but stubbornly resistant to direct detection by conventional means. Fast radio bursts cut through this invisibility by a different route, sensitive not to the temperature or the emission or the absorption of the gas, but simply to its electron content. And since the HIM is highly ionized and therefore composed largely of free electrons, it contributes to the dispersion measure of any fast radio burst passing through it, leaving a detectable fingerprint even in gas, too diffuse and too hot for any other technique to see. The detection and statistical analysis of this WHIM contribution to fast radio burst dispersion measures is already underway, using the growing catalog of localized bursts to constrain the fraction of cosmic baryons residing in this diffuse phase of the intergalactic medium. The results so far are consistent with the theoretical prediction that roughly half of all cosmic baryons reside in the HIM. The missing baryons are not truly missing, but merely hiding in a phase of matter that is extremely difficult to observe by any means other than FRB dispersion. This is a result of considerable significance for the baryon census of the universe, for models of galaxy formation and feedback, and for the interpretation of cosmological observations more broadly, because accurate accounting of where all the universe's ordinary matter resides is a prerequisite for interpreting the large-scale structure of the cosmos and for understanding how galaxies and clusters have evolved within it. The fact that fast radio bursts are providing this accounting, filling in a gap in the cosmic ledger that had persisted for decades, is a testament to the power of new observational windows and to the way that apparently narrow and specific discoveries, a millisecond radio pulse from a distant galaxy, can open onto questions of the broadest possible cosmological significance. The story of FRB, Arsenling Arsawanling Lobak Ishere, is, in this sense, a story about the nature of scientific discovery itself, about how a single observation, made with the right instrument at the right moment by a team with the right combination of technical capability and scientific vision can illuminate not just a single phenomenon, but an entire landscape of connected questions, pulling on a thread that leads through the physics of exotic compact objects, through the chemistry of the intergalactic medium, through the geometry of the cosmic web, through the history of the universe's expansion, and all the way to the most fundamental questions about what the universe is made of and how it came to be the way it is. This is what makes astronomy and astrophysics and cosmology such extraordinary enterprises, not merely the grandeur of their subject matter, though the grandeur is real and it is part of what draws people to these fields, but the way that they continually reveal unexpected connections. The way that studying one thing always seems to illuminate something else entirely, the way that the universe refuses to be divided into neat and separate compartments, and instead, presents itself as a seamless whole in which every part is connected to every other part by threads of physics and history that run through all of space and all of time. A millisecond pulse of radio waves from billion light years away is connected, through the physics of its production, to the interior of a neutron star 20 kilometers across. It is connected through the physics of its propagation to the distribution of matter across the entire observable universe. It is connected through the cosmological information it carries to the history of the universe's expansion over the past billion years. And it is connected through the human story of its detection and interpretation to centuries of astronomical tradition and to the future of an observational program that is only just beginning to realize its full potential. Every one of these connections is real, and following any one of them leads deeper into the fabric of the cosmos than the starting point could have suggested. There is a particular quality of attention that deep science requires, and cultivates an ability to hold multiple scales of thought simultaneously, to move fluidly between the microscopic and the cosmic, between the instantaneous and the eternal, between the technical and the philosophical, without losing the thread that connects them all. The fast radio burst researcher who sits down with a dispersion measure and a redshift measurement and polarization angle and begins the work of extracting cosmological information from those numbers must hold in mind at the same time the physics of the magnetar that produced the burst, the geometry of the cosmic web the burst traversed, the statistical properties of the ensemble of bursts needed to interpret the individual measurement, and the broader theoretical framework of cosmology within which all of these specific results must ultimately be situated. This breadth of simultaneous attention is what makes the field intellectually demanding and what makes its practitioners, at their best, some of the most nimble and comprehensive scientific thinkers of the current era. And it is what makes the story of FRB Ling Wan Ling Lu Bai Isha A not merely a story about one burst, or one detection, or one record broken, but a story about a way of seeing, a way of looking at the universe that is slowly, patiently, and with great technical ingenuity, teaching us to read the messages that have been traveling toward us across billions of light years of space, waiting for us to develop the ears to hear them and the minds to understand what they are saying.